first lecture. With me was to assist in this course is Mr. Zahir Abbas. He will be providing us very good and interesting contents about applied physics, which will be very helpful for all of us to learn and understand. So let's start, and we will be talking about these basics of physics, which comprises of the units, the physical quantities, and the vectors. Okay, the definition first. In definition, we'll see that the physics is basically the science of interaction of matter and energy. The definition is physics is the study of physical phenomena of the universe. It is experimental science, hence depends heavily on the objective observation and this measurements. So the objective observation and measurement is very important, and you can see that it's experimental sciences, heavily dependent on experiments, and through experiments you learn new things and get new knowledge. The standard and units: time, length, time, mass are the three fundamental quantities of physics. Then system, SI system, known as System International, is the most widely used system in the world, and it's in this system we know that length is measured in meters, time in seconds, and mass in kilograms. And you must have realized by now that normally in our real life we measure things in this spectrum, in these units. Okay, next. A physical quantity is measured in the terms of some standards, which is the unit of that physical quantity. It defines the magnitude. The unit defines the magnitude. For example, we have multiple systems available to us. That's MKS system, CGS system, and FPS system. You must have studied them in your school and college physics. And the name suggests that the length is measured in meters, mass in kilogram, and seconds, that is M, K, and S. Then CGS system, it's centimeter, the length, mass in grams, and time again in second. And FPS is foot, pound for mass, and second for time. So these are some popular systems and used in different areas. The prefixes: smaller units and larger units used for fundamental quantities. Let's have a look at the units of mass. You can see here that from the bottom I'm reading out, it's 1 kilometer is 10 raised to power 3 meter, that is 1000 meter. And if you check 1 centimeter, it's 10 raised to power minus 2 meter. 1 millimeter is 10 raised to power minus 3. 1 micro is 10 raised to power minus 6, and nano is 10 raised to power minus 9. We'll be discussing about this power of minus 9 or minus 6 and the positive. For mass, 1 microgram is 10 raised to power minus 9 kilograms, 1 milligram is 10 raised to power minus 6 kilogram, and 1 gram is 10 raised to power minus 3. And for second, we know that 1 nanosecond is 10 raised to power minus 9 seconds, 10 raised to power minus 6 seconds is micro, and 10 raised to power 3 is 1 millisecond. Okay. some of the base units, and these units are self-defined. As we have already seen the physical quantities of mass, length and time, and you know the meter of length is the unit of length is meter, mass is kilogram and second, and these are the symbols you use. There are also other physical quantities like electrical current, which is measured in amperes and with an A symbol, temperature, Kelvin in K symbol, amount of substance, mole, and luminous intensity is candela. So these are some basic physical units which are called base unit. Then we have some derived units. Derived units are produced, which are basically derived or obtained with the help of two or more fundamental units. Two or more fundamental units, the units we discussed in the previous slide. Here the area is measured in square meter. This is the symbol. Volume in cubic meter. This is the symbol. Speed meter per second. This is meter per second. Acceleration meter per second squared. You can see here. Weight, force, Newton, N, capital, pressure, Pascal, PA, and energy or work in joules. So these are the drive units, and as I have said earlier, you can see on the top of the screen are derived or obtained with the help of two or more fundamental units. Okay, let's talk about the prefixes and how do you see these numbers, the power increasing from 0 to 10 raised to the power 24 and onwards. Okay, let's see. At the bottom you can see it's 10 raised to the power 0, which means it's 1, so there is no prefix for this particular thing. Then we have deca. Deca is the numerical multiplier is 10, and 10 raised to the power 1 is 10. Then hecto and kilo. Hecto is 100, kilo is 1000. This is where you are going to start normally in your numericals. So then okay, so we have this kilo, that is 10 raised to the power 3. Moving forward and upward, we can see here that mega is 10 raised to the power 6, then tera is 10 raised to the power 9, peta is 10 raised to the power 12, exa is 10 raised to the power 18, zeta is 10 raised to the power 21, and 10 raised to the power 24 is iota. So these are the exponential multipliers. Okay. For the negative power, the exponential multiplier, we have decimal, deci, that is 0.1, 10 raised to the power minus 1. Then we have centi, it's 10 raised to the power minus 2. Milli is 10 raised to the power minus 3. Micro is 10 raised to the power minus 6. Nano 10 raised to the power 9. Pico is 10 raised to the power 12. Femto 10 raised to the power 15. Atto 10 raised to the power 18. Zepto 10 raised to the power 21, and Yocto is 10 raised to the power 24. So you see the exponential multiplier increasing in the negative. Negative will give you this. These are the names. The commonly used are centi, milli, micro, nano, and pico. And once you start using them, you will remember everything. Next, uncertainty and the significant figures. Now we are going to discuss something about significant figures and what is the purpose and what is the use of them. The uncertainty of a measured quantity is indicated by the number of significant figures. For multiplication and division, the answer can have no more significant figures than the smallest number of the significant figures in the factors. For addition and subtraction, the significant figures is defined by the term having the fewest digit to the right of the decimal point. You can see a very small error can create very big error results, mishaps and results. So error can be very small but can be very destructive for our results. Indicate precision of a measured value. The significant figures indicates the precision, the accuracy. So let's say if I say that the outside temperature for now is 35 degrees centigrade and someone else told you that it's 35.5, so which one is more accurate, the 35 degree or 35.5 degrees? Correct, the one with the decimal points. So for more precise measured value, you need to have decimal points. Determining the significant can be tricky. There are some very basic rules, but the main thing is that you keep practicing. If you practice, only then you will be able to follow it and use it. Let's use and see some significant figures and how to interpret them. Let's begin with this example of 4.337. You can see that all the non-zero digits will be considered as significant figures. Remember, all the non-zero digits. Okay, if you have a leading zeros like in this figure, you can see that it's 0.00065. You have zeros on the left side. You can see the zeros on the left side. So what you do is you ignore all the zeros on the left side to count the significant figures, and the remaining two will be counted as significant figures in this particular example. Moving on to the next example, here we can see it's 1.000023. Now remember that if the zeros are kept between two non-zeros numbers on those both sides, left and right, they are in between two or more than two non-zero numbers, then all the zeros will also be counted, and you can see that there are 7 significant figures because we are counting zero. We are not ignoring zeros in this particular example. Alright, then the trailing zeros, here you can see in this example 89.00. For this you are going to just ignore the zeros which are present after the decimal point on the right side. So the significant figure is 2. Another example, it's 8900 without any decimal point, because there is no decimal point, or if you put a decimal point here for clarification, then the zeros on the left of the decimal point after any non-zero number, then all the zeros will be counted, and it's now 4 here. You can see the example. Okay, next is leading, captive and trailing zeros. Here you see example, it's 0.003020. So using the rules discussed above, you can combine all the rules and figure out that the significant figures is 3, because we are going to ignore the 0 on the right side and all the zeros on the left side. Similarly, if you have a value 3020, then it will be before the counting of significant figures. For scientific notation, the significant values are counted before multiply by 10, and that is 7.76. Here in this example, 7.76 into 10 raised to power 3, so we have 3 is the count of significant figures, and all the rules applies accordingly. You have to remember, it's not very difficult, but you have to remember these rules before using. Calculating with significant figures for multiplication, the number that has fewest significant figures, that is how many significant figures should be in your answer. For example, if you are multiplying 3.35 multiplied by 4.669 ml, the answer is 15.57115 ml, and if you rounding it off, then rounding will be making it 15.6 milliliter. Explanation of this is that 3.35 has only 3 significant figures, as you can see, so that's how many should be in the answer. Rounding it off to a 15.6, which also carries 3 significant figures. For addition and subtraction, find the number that has the fewest digit in the right to the right of the decimal point. The answer must contain no more digits to the right of the decimal point than the number in the problem. Alright, so let's see an example here. 64.25 centimeters plus 5.33 centimeters is equals to 69.583 centimeters, and rounding it again, it becomes 69.58, ignoring the last 3. Has only 2 significant digits to the right of the decimal point, that is 64 before decimal point, so that's how many should be in the on the right to the decimal point in the answer. Drop the last digit, so the answer is, so again 25, only 2 significant digit after decimal point, so answer should also carry only 2 significant digits. Alright, that is, all equation must be dimensionally consistent. Be sure you are using your proper units, that is, if you are adding apples, then all the apples, you cannot add apples with oranges, you have to add apples to apples. See, always carry your units throughout the calculation. You have to make sure that the unit you are using in your numericals, in your calculations, are consistent. How many meters in a kilogram? Anybody? That is 1000. Right? Okay. Scientific notation: the number expressed as the product of a number between 1 and 10 and a power of 10. Meaning 7.63 into 10 raised to power 4 means that this 10 raised to power 4 is 10 multiplied 4 times, like 10 and 10 and 10 and 10. Or you can say that it's 1 with 4 zeros, or 10,000. So always has one non-zero digit to the left of the decimal point. I'm talking about scientific notations. They have always at least one, always has one non-zero digit to the left of the decimal point. Only significant numbers are used as the first number. First number can be positive or negative, power can be positive or negative. These are the basic criteria which you need to remember. Power of 10, I know everybody should know this, is 10 to the power 1 is 10, then 10 to the power 2 is 10 multiplied by 10 is 100, 10 to the power 3 means 3 times 10, 10 into 10 into 10 makes 1000, then 10 to the power 4 is 10, 10, 10, 10, that is 10,000, and of course you know 10 to the power 0 is 1. For the negative powers, we can see that 10 to the power minus 1 is 0.1, 10 to the power minus 2 is 0.01, 10 to the minus 3 is 10 to 0.001, and 10 raised to 4 minus 4 is 0.0001. You can check out these calculations if you want. Converting from standard to scientific notation. If you want to convert some number from a standard notation to a scientific notation, it's simple. Move the decimal point until it is behind the first significant digit. If you have a number like here 228.5, you will move your decimal point to the after the first 2. The power of 10 is the number of spaces between the decimal points moved. Decimal moves to the left, the exponent is positive. Decimal moves right, the exponent is negative. This is simple. So if you have a 222.5, you move 2 places and it becomes 2.285 into 10 raised to power 2. You move 2 places, you have a power of 2. Decimal places move 2 spots on the left side. That is why it's positive. And if you see here that we have a number 0.0002285, you start moving, but in this case you have to move towards the right direction, and you will again place your dot here between 2 and 2. So how many spots you move on the right side? It's 1 2 3 4. So power of 10 will be -4, and this will be the number. So it's going to be 2.285 into 10 raised to power -4. The staircase method is very useful for converting between different units. This is the basic unit. If you want to convert to a smaller unit, that is, you are moving the decimal point to the right side, what you do is you multiply. Remember this is going to be very handy and very useful for you. And if you are moving to the left side, then you divide by 1000 normally. If you are using this system, I mean that if you have 1 kilogram and you want to convert it to grams, that is, you want to move to the right side, what happens is you multiply by 1000. Simply, if you have 1000 grams and you want to convert it to kilograms, that is a larger unit, you will be dividing it by 1000. So this is a good thing to remember. Now you want to convert 3.5 hours to seconds, and you must know the basics that every hour has 60 minutes and every minute has 60 seconds. So 3.5 will be multiplied by 60 upon 1, that is 60 minutes and in 1 hour, and again multiplied by 60 seconds, that is 60 seconds in 1. So you get 12,600 seconds, and if you just approximate it, round it, then it's become to 2 significant figures. Especially this is the thing, if you want to appropriate number of a significant digits 2, then it's 13000, and you can see 13 are the 2 significant digits. Conversion, few more conversions. You can see kilogram for mass is 2.2046, 1 pound is 0.4536 kilograms, 1 ounce is 28.35 grams. Don't need to remember this, but you should know the scales and the conversions, the basics. For area, 1 square meter is equals to 1.196 square yard, 1 square centimeter is 0.155 square inches, and 1 square kilometer is 0.386 square miles. For length, you can see 1 meter is 1.093 yards or 3.281 feet. Kilometer is 0.621 miles. Mile 1.609 kilometer. Foot is 12 inches. 1 yard is 3 feet. 1 furlong is 220 yards, and 1 knot is 1.852 kilometers. Time for solar year, we know that we normally say that it's 365 days in each year. Every year we have 365, then 365, and the 4th year, which is called leap year has 366 days, but actually in reality every year has 365.24 days. But normally we cannot count in our calendars a quarter day, so what we do is we lag behind for 3 years, and then synchronize ourselves with the system, the solar system, and it becomes 366. So these are few things. Okay, that is it for today. We are going to discuss the vectors in the next lecture. I hope you understand and follow the basics, but if you have any questions you can ask me. Thank you very much. Allah Hafiz.